Hello everyone. Yesterday we talked about, let me quickly open up the summary, the notes that we keep building on. We've talked about, I like to quickly go through the set of notes that we have. And so we have the integers, which are positive, the subset of the integers. We have positive integers or natural integers. Natural numbers include the 0, and basically natural numbers are non-negative numbers. We have a list of real numbers, basically everything. We have a proper subset and a normal subset. A proper subset when you have a superset that contains an element that's not in its subset, and the empty list is always a subset of a list. There's always that. The cardinality is the number of elements or the order. The order of a set is the cardinality or the number of elements. We knew how to get the number of elements, which is 2 to the power of n. 2 to the power of n. So n being the number of elements within the set. And we also came to know that if we want to get the number of subsets in a set, taking a given number of elements within the set, we use what's called the factorial. And so 2 to the power of n, that's the number of combinations or the number of subsets. And for a proper subset, we just subtract the 1. Anyways, 1 is not a prime number. Prime number starts from 2. We also know that, what else? A set of one element has 2 subsets, the empty set and the element itself. Okay, this is the symbol for the number of combinations given k, given the number of elements. We know the union, the intersection, the subtraction, the universal set, the complement. We all know what that is. Union is all the elements. The subtraction, you basically deduct the elements that are not meant to be. And for the intersection, you basically include the common elements, the AND operator, if that's the right. So we also know the conventions used to include the sets and subsets. And that's fine. We also know the cardinal number of the union of the two finite cities. So this is the cardinal number, basically a, b minus a intersecting b, and then the number of elements. The cardinal, remember, the cardinal is the order or the number of elements. So in that sense, to get the number of elements in A union B, you take the elements of A and the elements of B, and then you subtract the intersection. So if you want to get the intersection, you just move these about, basically the polynomial operations, functions. We already know the commutative and associative is shared among union, intersection, and this is the symmetric difference. The symmetric difference is basically the exclusive or elements that exist but not in both, exclusive or. Elements in A and B but not in both. So the symbol is either delta or this symbol here. That's something is worth noting. And then the other most important, the equation for the symmetric difference is either A union B minus the intersection, or A minus B union B minus A. You basically remove whatever it is in between. So that's that. We've already seen how is that possible with the 3 sets. You basically, if you have a 3 sets, the union of the symmetric difference of 3 sets. So you solve for 2 because given it's an associative and commutative, given the associative and commutative properties, so you solve for 2, and then the result you solve it with a third set, and that's how you get the symmetric difference for 3 sets. Anyways, the other most important topic we advanced to was the domain and the range. So the domain is basically the set of independent variables that you use to solve for an equation that would result in what's called a range, or the image or the images. So the result is the range, which is the result of applying an independent variable to a given function. Now, there is a difference between a function and a mapping. Now, a function has basically two main properties, is that every element within the set can be mapped to an element within the corresponding set. Basically, what it means in layman's term, every variable you apply to a function has to have an output. Single output, which is the second requirement. Each element should have a single output. No two elements should point to the same input. That's what it is. Basically, and if you can see the graphs here, there is a single value of x, and then there's always, whenever you take an x, you get a different value. So this is not a function. It's more like a mapping. And this is also not a function because you have two intersecting points. So there are two values for the same value of x. You can get two values, which is not a function. And then the other topic we've advanced to was the composition of functions. So you have a composition of f and g. So you start off with the right-hand side. Use the right-hand side and apply it to g. Something to note is that you have to consider the domains within this. The domain of the first input has to be inherited by the second function, the composition. And this is not to be confused with the dot, because this is a composition while the dot is a number multiplication. And there's something else with the notations that you should consider, is that so you have a function for natural numbers yield to natural numbers. So this is the domain and this is the codomain. The function f has a domain of n, the natural numbers, and a codomain of n, which is also the natural numbers. So the result of y, or the range, is the same category of the input of the domain. Now, in this case here, there's this drawing here. You have a function. X would point to x squared. So this has to be x squared here, because we'll just minimize it here so that it's visible to us. So as you can see here, now this is x, which is the domain. Now takes x and returns x squared. So the function of x, so this is the function of x, it takes x and then yields x squared. This is the easy way to remember it, but this is also something one should consider, because you never know what the literature throws at your face. So this is the difference between the symbol of the arrow here. There's this arrow here with a notch here or something. Yeah. So x would return x squared. So you apply x to a function and then you get x squared. You apply x to a function, that's what you'll be getting. You're getting an x squared. So the range of f, this is denoted by Rain or Dominic. Anyway, so yeah, logs are undefined for 0 or negative values. Square root of 0 is undefined for negative numbers, only not the 0. So notice here the less than. So the square root of negative numbers is undefined for the square root, and for the logarithms, it's for 0 or negative numbers. So this is important for you because the composition of functions mandates it mandates that you know the domains for each function, because that's how you would define the sets associated with a given function. It's very important because if you're working with domains on functions and sets, you have to have the domain has to be bound to, because assuming you're working with a square root, the function takes a square root without you defining the domain. Then what if someone takes in by default, it will assume a natural number or real numbers. So what if, assuming by default, the person whoever is reading your algorithm might assume that you're dealing with real numbers. Yeah. So what if the person opts for a negative number? What's then? Now that's the thing. I mean, the square root is undefined for negative numbers. So it's very important that when you do these considerations, you specify the domains so that you won't get into trouble, or the reader won't get into trouble, because it can get confusing at times. Now, the second most important topic that we should be covering is what we call injective, surjective, and bijective. We've talked briefly about this in the last session. which mainly means that once you have the it's just the way A corresponds to the codomain. So at times you have all the elements in A point to an element in B, regardless of the so you have different, like we have 5 scenarios here. We have A points to every element in B, while B, or the cardinality of B is more than the cardinality of A. In that sense, A has two values. A has two values, and we know that if A corresponds to more than a single value, it's not a function. Now, we could have like two A's point to a single B, that's fine, that's a function, but in this case, it's not a function. Now, in this case, you get all the elements in A point to a single element in B. Now, this case here, this one here, suffices the function rule. And it's not necessarily that every element in B has a mapping with A. So in this case, this is a function. Now, moving on to a different case where so this is injective. So all of the elements point to a single element in B. And in this case, you have a single element point, a single element. Now this is so it's pointing to a B, but two values in A point to B. And then you have, in this case, you have a mixture of, now all of these elements are being pointed to by A. Now every B has some A, so B can't have many A. Okay, so it's quite clear now. So it's not about the number of arrows, it's more like the number of connections from B to A and A to B. Basically how many B's are connected and how many A's are unconnected. In this case, all the A's are connected with B's, but there's a remaining one, so this is a function, but at the same time, now B has multiple A's, so this could be surjective. Every B. Now it's not every B, so there's a B, there's a random B here, so this is not surjective. Injective. So we need a way to remember these terms. So we have injective, surjective, and bijective. Bijective is fine, it's understandable given the bi here. Now surjective, it means, surjective, you have more than a single injection, like surplus. So in this case, B can have multiple A's. Every B has some A. It can have one or more A's. Injective, B can only have a single A. Okay. So a general function points from each element of B to B, from A to B. It never has one A pointing to more than B, so one to many is not okay in a function. That is correct. But more than A can point to the same B. Many to one is fine, but not one to many. Yeah. Injective means we don't have two or more A's pointing to the same B. So many to one is not okay. This is injective. As it also a function, one to many is not okay. But we can have B without a matching A, one to one. Injective is called one to one. Surjective, that means that every B, is very important, that every B has at least one matching A. Must be more than one. There won't be an A left out. Surjective. Okay. Bijective means both injective and surjective together. So there is a perfect one-to-one correspondence between the members of the set. But don't get that confused with the term one-to-one used with the injective, because in this case, now every element is pointed at by A, but at the same time, with the injective, you can have an empty B somewhere here. Okay, bijective functions have an inverse. If every A goes to a unique B, every B has a matching A, then we can go back and forth between without being led astray. Yeah. So these are the inverse functions, huh? Should explore them. Now let's see a few examples to understand what is going on. When A and B are subsets of real numbers, we can graph the relationship. Uh, Let us have A on the x-axis, so this is A, and B on the y. And look at our first example. Now, in this case, it's not a function because it has multiple intersections. A single value for x has two values for y. This is not a function because we have an A with many B's. It's like saying, yeah, it fails the vertical line test, so not a function. But it's still a valid relationship, so don't don't get angry with it. Yeah, it is a mapping, yeah. Now a general function can be like this. Now this is a function because every x can have a single b, every a has a corresponding b, and that's it. But there might be some a's can be the same. Yeah, so we have points here, x's. Now we got two different x's pointing to the same y, so that's fine. It can possibly have a b with many a's, yeah. Example, sine and cosine, etc. like that, perfectly valid functions. But in injective, now the injective has more stricter of a rule. B can be empty at some point, like you can have an empty B, but every A has to have an element a single way, so one-to-one relationship, every element in A. Now, every element in A can only have one element in B. In fact, we can do a horizontal line test. To be an injective horizontal line test should never intersect the curve at two or more points. The horizontal line test. So yeah, so the horizontal. So we have the vertical line test and the horizontal line test. Strictly increasing and strictly decreasing functions are injective. You might like to read about them for more details. Yeah, we could. Strictly increasing and strictly decreasing. It seems like there's always a one way up, one way down. Okay, and there we are. This is the inverse function. Yeah, we could learn more about it. Then we just stick to okay. Alright, so if it passes the vertical line test, it's a function. If it passes the horizontal line test, it's an injective function. This is interesting. I should copy this. Oops. Alright, so we could copy this to here. Yeah, we could get rid of this. It's an injective function. Right. Stand by for more details about all of this. Injective, a function f is injective if and only if whenever f of x equals f of y, x equals y. F of x is x plus 5. The set of real numbers R to R. Is it true that whenever f of x equals f of y, x equals y? Well, sometimes y doesn't have an x, then 3 plus 5 equals 8. F of y equals 8. What is the value of y? It can only be 3. Yeah. F of x. And this is it true that whenever f of x equals f of y? Okay. X equals y. Yeah, because regardless of the value you're putting in, f of x. Yeah, because if you try to solve assuming f of x is y, so assuming y is 8, 8 equals x plus 5, you need to find the x, so you take on the x to the other side, and then 8 minus 3 is actually 3, that's the x equals 3. F of y equals 8. Yeah, in this case, if it equals the same function, then it's 3. Y would be 3. Okay. Example 2, f of x equals x squared. The set of real numbers r to r, so both are real numbers. It's not an inductive function because of this kind of thing. F of 2 equals 4 to the power of 2, that's 4. And if f minus 2 equals 4, so you get two different x's pointing to the same. It's a valid function, but it's pointing to the same y, which is unacceptable in injection, in having an injective relationship. X equals y because f of 2, but 2 does not equal minus 2. In other words, there are two values of a pointing to b. But if we made it from the set of natural numbers, so natural numbers, then it's injective because f natural numbers are positive, including the 0. So f2 is 4. There is no negative 2 in the list of natural numbers. Okay, so the domain and codomain are important. Okay, it's called onto. So the surjective, a single value of b can have more than a. From set A to B is surjective if and only if every y in B is at least one x in A such that f of x equals y. In other words, f is surjective if and only if f of a equals b. In simple terms, every b has some a. Right, every b has some a. Right, so f of x equals y. In other words, f is surjective if and only if f of a equals b. Function f from set A to B, okay, is surjective if and only if for every y in B there is at least one x in A. Yes, such that f of x equals y. In other words, f is surjective if and only if f of a equals b. Okay. Every b has some a. Example, the function f of x equals 2x from the set of natural numbers n. Natural numbers, not real numbers. To the set of non-negative even numbers is a surjective function. Wait a second. Is a surjective function? Set of non-negative even numbers. How is this surjective, mate? 2x, yeah. Because whatever the number you supply in x, it's always multiplied by 2, rendering it an even number. So every element in the corresponding codomain would have at least one mapping from A or whatever, or X. So that is surjective. It could lead to the same value resulting in the same number, but like as in what is it? Which number could it be? I'm not sure. Anyway, so but f of x to x from the set of natural numbers to natural numbers is not surjective because you can have negatives here. No number in n can be mapped to natural numbers. You can have set of natural numbers being mapped to what do you call it, natural numbers. You can have negatives and real numbers, and odd numbers as well. No member in N can be mapped to 3 by this function, and it's mandated in surjective that each and every element in B, unlike injective. Now, bijective, a function f from A to B, is bijective if for every y in B there's exactly one x in A, such that f of x equals y. If bijective if it's a one-to-one correspondence between those sets. In other words, both injective and surjective. Remember, surjective mandates that each element should have a correspondence, and injective mandates that each element should have only one correspondence. And in that sense, in this case, to suffice bijective, all the elements should be pointing to something, should have a correspondence, and only one correspondent. So we have a function here of x squared from the set of positive real numbers to positive real numbers. So yeah, it's both injective and surjective, thus this also is bijective. But the same function from the set of all real numbers. So of all C numbers, not bijective because we could have so we have two numbers lead to the same value. Now this is the interesting part, the exercises. This gotta be, I know this site is really good because they kind of complicate the exercises at times. They use some weird terminologies that not like really weird terminologies, but they use some notions that mandates you study more about the subject until you really get the hang of it. Alright, so on with the sets at all. So let's do this. So what kind of function is this? So we have, let's explore this. We have an empty B, so this is definitely not a bijective and not surjective. This is an actual function, and it's also injective. One-to-one, general function. It's both. It's a general function, yet it's not. It's injective though. It's a function, so every member of A has its unique matching member in B. It's not one-to-many or many-to-one, but there is a B without a matching A. This is injective but not surjective. Next, so a functions from set A to set B this is an actual function, so we know it's a general function, but now A to B. Now I just want to test out what happens when I click on. I know this is like surjective, and is also, no, this is surjective and bijective as well. It's bijective, a one-to-one correspondence, but not subjective, injective. No, this is not an injective relationship because, no, it can be. So it's bijective, but so my answer here is D, but I want to see this. Good try, but A is not right. D is the right answer. Read why. There is a perfect correspondent, one-to-one correspondence between the members of the set. So it's bijective, both injective and surjective together. What if this not the right answer? Not the right answer. Alright, next question. The function from set A to set B. So this is an injective here, and it is subjective. No, it's not subjective because there is an empty set here. So it's a general function. It's a one-to-many relationship, but is many to one. One more than A can point the same B. This is a general function. This is not one-to-many, but is many to one. Yeah. If it was one-to-many, it won't be a function. The function from set A to set B is, now we have more A's. Now this is definitely surjective, and it can also be, no, surjective. It's not bijective because bijective mandates that there's only one connection. Okay, so in this case, this is injective for sure. multiple values. This is not a function. Wait a second. A single value in A different values. It's many to one. That's fine. So this is injective, and it could also be general function. No, this is injective. You choose B, but A is correct. There is not one to many, but many to one. So why is it not injective? This is not one to many. It would be a function. What is it? So we have more than one, and every element in A is pointing. Oh man, injective has to mandate that it's only one connection. Okay, so we have here every element in A is pointing to an element in B. There are no two connections in B. So this could be surjective. This could be surjective. Only one correspondence. Could be bijective, yeah. Both together. Okay, so in this case, no, this is not bijective, and this is definitely not surjective. This is injective. Many to one. Oh my god, I keep forgetting that you should only have one connection when it's injective. My bad. So this is injective. Alright, which of the following function is not injective? Okay. Not injective. Not injective. Well, definitely. So -3. So this is injective. So there's always a single value because it's squared. So whatever the value, all the squares here. So all of these are actually injective, both A and B. Now, for the natural numbers, no, wait a sec. Yeah, both are injective. And this one is also injective because, no. Yeah, it's actually injective. You could only have a single value. But this one is not injective because it's real numbers. The negatives would become positives. And then you could consider for example, x squared, so x equals 4. This is the only one possible answer in the set of real numbers. Now if it's squared, you would have multiple values. Which of the following function is not injective? Now the cosine of x from 0 to 180 in real numbers. Tan. Now I'm not familiar with the cosine and sine just yet and tan and stuff. But if I'm not mistaken, this is cosine from 0 to 180. It's like positive in R. 1 to 360 x cosine x 1 and -1. I don't think this is injective here. And then from 1 to 80 is injective because every member x in 0 has a unique value for cosine, which is a real number. Cosine from 0 to 180 is injective because every member in x has a unique value for cosine, which is a real number between -1 and 1 inclusive. R is not injective because every member in x does not have a unique value for example, cosine 60 is 0.5, and cosine 300 is 0.5. So let's check out the quiz results. I've got 3 and 1 done on purpose, so it's 2 wrong. Nice, so this is out of the way. Done the exercises, but we need to study more about the cosine and the sine. But I think we're done, we're through with this. So we have the inverse functions. So inverse functions go the other way. Let's start with the example. Here we have a function f of x, 2x plus 3. Now anything else, anything of importance that we should add here? This is really interesting because I think the graph is the best way to really understand this. I mean, enable some images, whatever. Let's copy the source of this with the bijective to the here. Now we could go like that's not dismiss. So injective, this is done out of the way. We have the function f of x equal to x plus 3 written as 2x plus 3. Multiply by 2 and then you add 3. Fine. The inverse of the function goes the other way. Okay. So this is considered y. So y minus 3 divided by 2. Oh, so basically it's like you kind of solve for it. It's usually shown by putting the negative 1 at the top after the function name, like this. We say f inverse of y. So the inverse of f of x equals 2x plus 3 would be written as fx minus 3 over 2. I also used y instead of x to show that we are using a different value. Alright, back to where we started. The cool thing about the inverse is that it should give us back the original value. When the function f turns the apple into a banana, the inverse turns the banana back into an apple. Okay. Interesting terminology. Using the formulas from above, we can start with x equals 4. So that's 11. We can use the inverse on the 11. Minus 3 divided by 2, that's 4. Okay, so applying f and then its inverse gives us the original value back. We could also have put the functions in the other order, and still works. Yeah. So we can work out the inverse using algebra. Yeah, so put y for x, then you solve. That's how I did it. Fahrenheit to Celsius. To convert Fahrenheit to Celsius, you have f minus h2 multiplied by 5 or 9. The inverse would be you divide by 1 second. So the inverse would be you multiply by 9 over 5. You move this to the other side, so that's like 9 out of 5. And then plus 32. Inverses of common functions. It has been easy so far because we know the inverse of multiply is divide and the inverse of add is subtract. But what about the other function? So what did he do here? Did he like just inverse the symbols? Minus and divide. Yeah, so it's like he divided by 2 minus 3. Yeah, just it flipped like the symbols, but I did it algebraically. Multiplication equals x is okay, x to the power of n. E to the x is log, a to the x is log ay, sine inverse. Yeah, we should read about the sine and cosine here. Careful, did you see the careful column above? Yeah. Y is not a zero, greater than or equal 0. Yeah, there's non-negative numbers. I don't think we really have to memorize this. When we square a negative number and then do the inverse, this happens. But we didn't get the original value back, we got 2 instead of negative 2. But for not being careful, so the square root function says does not have an inverse. We can fix that, restrict the domain. You need the unique values. Just think, if there are 2 or more values x and y, how do we know which one choose going back? So in this case, the injective functions are not reversible. And sorry, the surjective, I mean, the surjective and bijective. No, sorry. It's just the surjective. Yeah, it's just the surjective. We can take a look. All elements. Only bijective functions have an inverse. The main is all the values of the unit function. The range of values come out. As it stands, the function above does not have an inverse because some y values will have more than 1x, because you have a crossing here, the vertical crossing. Like you can't have multiple x values resulting in the same y value. Restrict the domain and get rid of this side and this side that could duplicate the values. So it's unique for every y. Now we can have an inverse. Now this, if x goes from the domain to the range, the inverse the function from the range back to the domain. Yeah. Let's plot both in terms of x. So it's now not of f inverse of x, not f of y. So you have this inverse and then you have this inverse. Like a mirror image is flipped about the diagonal. Okay. Are symmetric across the line y. This is like super duper interesting. We really should revisit this on the next video because I think this is critical. Alright, let's stop here and then pick this up on the next session. Thank you for tuning in. Have a good day.